Do you have any questions? Well, last time we went over the single stop matching concept very quickly using the Smith chart. And also we saw the equations that we can use in this regard as well. I believe we did the equation in an earlier lecture. And the whole idea is that we would like to move away from the load until a location where we match, when we match the real part. And after we match the real part, what's left in the matching process is the imaginary part, which can be taken care of using reactance. Right? Using a reactance means another transmission line, which we call the stub, and we use that stub to produce the reactance that we need. So we take care of the resistance by moving down the line until a particular location. Once we are in that location, the resistive part or the real part is taken care of. The reactive part is then can be taken care of by adding either a series reactance or a shunt reactance. And once we tune, then we are down to Z0. The schematic that we usually draw is like this, but this is a simplified schematic that often we do so we can get over drawing nodes and lines crossing each other and all that. Basically, here's your transmission media, all right? Which can work as well for waveguides when we talk about it, because the waveguide doesn't have two wires, right? The waveguide is simply a transmission media, right? So you have a transmission media, and somewhere in here you add a stub. And in this case, it's a shunt stub, and the stub is shorted there. So this is a simplified version of the schematic that we see up there. So the point is, at this location here, we have an impedance which we call Z1. At this location here, supposedly the impedance now has become Z0. All right? And Z0 is going to be matching this, the combination between Z1 and what we have here as Z of the stub. All right? If I call it ZS, it would be ZST. All right? Because ZS is typically the source impedance, right? Z of the stub. So, Z of the stub is the input impedance of the stub length LS, short circuited here, for example, or open circuit, all right? And gamma S and Z naught S, these are the characteristics of the line itself, and this would be the impedance here, Z of the stub. Z1 would be, if I may draw it on the other side, Z1 would be ZL seen through Z0 of the line after a distance D where the stub is going to be located, and that's going to be Z1. If you write this equation here for Z1, you write the equation there for Z stub, combine them together and equate them to Z0, you have enough equations to solve for the unknowns, right? So how do we do that on the transmission, on the Smith chart? We do this one first, and then we do this one next. So Z1 is supposed to be pure reactive. And the resistance, I'm sorry, not pure reactive. I'm not well. let's say the right thing here, right? The real part is matched. And there will be some reactive part. This is supposed to be pure reactive, that's what I meant to say. And the reactance tunes the Z1 reactance. That's the whole principle there. Okay? So this is the whole principle. So in the Smith chart, if the shunt, that means we work with admittances, right? We said that last time. It's best to work with admittances, so instead of Z1 I work with Y1. It's equal to G1 plus JB1. And obviously in that regard, this has to be a minus JB1. That's JB of the stub, should be minus JB1, such that when you add them together, they cancel each other, and the G1 in this case must equal to the G naught, okay, which is 1 over R naught. Okay? So if the real part is matched, that means the G1 should be matched. So how do we do that on the Smith chart? Here's our Smith chart. This is the R equals 1 circle. The real part is matched here, right? The real part is 1. That means when you normalize Y1 or any impedance by Z naught, you get a 1 for the real part. So this circle here is the locus of matched real part. If you work impedance, and obviously that's R1. If you work admittance, then that's also G is equal to 1. Because we mentioned that Smith chart can be used for impedance or admittance. The only difference is, if you work with impedance, then your point on the chart represents gamma. If you work with admittance, your point on the chart represents minus gamma, right? Minus gamma. So, suppose I start with a Z load right here. Let me get some other color. That means if I take this on the fixed radius circle, right? That would be my Y of the load. This should be obviously normalized, okay? I'm going to add N to indicate that these numbers are normalized. You can't work ohms on the chart, right? The chart has no units. It's all normalized quantities. So you need to work normalized. So step number 1, if you want to write them steps, ZL over Z naught gives ZL normalized. Okay. Step 2, that's equal to RL plus JXL. Locate RL and XL on chart. That's supposed to give you gamma sub L. If you like, this is your gamma sub L. This phasor here is gamma sub L. Magnitude and phase. Step number 3, locate minus gamma sub L. And that's obviously, that gives you Y sub L normalized, which is GL with JBL. So this one here is GL plus JBL. Next, we move towards the generator. Move towards generator, and that's clockwise, right? So move on, it's lossless, right? We are assuming lossless. So the motion is going to be on a constant radius circle. The circle here would not be the same if I have losses, right? It would be a spiral. Lossless means constant gamma circle. So I'll move on this one here until I match the real part. In other words, intersect or intercept, whichever way. G is equal to 1 circle. And obviously, I have several possibilities. Use one solution, solution number 1. I can go on, solution number 2. Obviously, there's also solution number 3 and 4 and 5 and 6, etc., right? So that's actually 3, 5, and that's 2, 4, 6, right? You can keep adding half a wavelength and get back to the same values. So if you are moving away from the load and you have a construction issue and you can't work on your line at this point, then it doesn't make a big complication if I move another half a wavelength and work where things can be worked out. So sometimes your antenna is up a tower and your location that you want to work on is somewhere in the middle of the tower and you want it to be more convenient, so it's okay to move another half a wavelength or 2. You don't want to go too far because, again, if there are losses, you wouldn't be exactly on a circle, right? The spiral may be kind of close, but obviously the further you go, the further you add errors. So you don't want to go too far. So these are the two possible solutions. Okay? What do we do here? We get Y1. Read Y1. We can call them 1 and Y1, 2. We said solutions 1 and 2, right? That's going to be 1 in both cases. The real part will be 1 in either case. One of them will be a plus JB, the other one will be logically minus JB, right? One of them will be the opposite of the other because of the symmetry. So Y1 solution 1 is there, Y1 solution 2 is there. The way we have it is the upper one is a negative solution, and the lower one is a positive solution, and this one is a negative solution. We read that, that means we'll go to the step. Step 5, Y stop is equal to minus Y11 or minus Y12. So there's Y stop 1, Y stop 2. There are two possible solutions. Either negative the first one or negative the other one. Because the real part is 0 anyway. it should be, okay, y1 conjugate. No. Let's write it JB11 and JB stub 1. So JB stub 2 is equal to minus JB1, and this one here is minus JB1. In either case, it should tune out. There was another step in between, but that's okay, we'll get back to it. Now, step 6, work out the stub problem on a separate chart. Stub chart. We're starting with a zero impedance, a short circuit. So this one here is Z short circuit. Right there. So that would be Y short circuit. So work the stop chart. Start at short circuit end. Step 7. Move towards what? We're moving towards what this way? It's away from the load than it is towards the generator. Till we get the value that we need here. It's a minus JB1 in this case. Where's minus JB1? Somewhere in here. Minus JB1. Till minus JB1. Or till, let me write that in different color. Use a white. Or till minus JB1, which is a plus JB1, right? So the other option is to continue going until you get to that. So these are the two possible scenarios. This is solution case 1, and this is solution case number 2. Supposedly we have match now. How much is LS? How much is DS? That will be read from the chart. DS was the distance from YL to this location. So the distance from, what kind of color can I use now? I haven't used this. So the distance from here to there was the first possible distance here. That's DS1. So I have step 5 twice here. Okay. So somewhere in here, for A, read DS1 and DS2. DS2 would be from here to the second solution. So this would be DS2. How much is LS? The distance from here to there. That's LS1. How much is LS2 from here all the way to there? LS2. So step 8, read LS1 and LS2. Now, you can do this by programming this in MATLAB or MATCAD or Mathematica or any of these packages, or even some of those microwave design system packages. But you wouldn't have the feel for numbers. You get some numbers and you have no insight whether they are right or wrong or how much error or what have you. If you work like this on the chart, and you still have a mismatch, you can see how much error you have here, how much error you have there, and whether you are close enough here, for example, that the distance is not accurate to read, that kind of thing. You can see visually, right? You realize that, if you have a curve like this and you do intercept, you can get a clear number here. But depending on the slope, the intercept may be kind of vague and you have some range of numbers, right? So the visual is very useful in this case, right? So don't discredit this approach and say, well, we have modern equipment, or we have modern tools, or what have you. Still, the visual is very important. Now, the designers like this very much because it gives them room to variation. Sometimes, you get stuck with some of the numbers that you get from the calculations and you don't know how much you can tolerate, right? So it becomes useful in this regard. Now, as it turns out that there are impedances that you cannot match using this approach. Right? A single stub tuner is not guaranteed to match all sorts of impedances. Right? And that could be a good question for you to investigate on your own. As it turned out that you can guarantee that you can match any impedance there is if you use 3 stubs. Right? 3 stubs on a line can guarantee that you match any impedance that you care to have. Right? And that's an exercise that we usually assign as a homework, but I'm not going to do that this time because we're kind of behind. I don't want to get consumed in that. But it's something interesting for you to investigate. So go to your references and check them out. Any questions on this before I erase that? Yes?
It doesn't really have to do with that, but what's the Q of these networks?
What's the Q? That's a very good question, right? The quality Q is a quality factor, okay? And it is basically an indicator of how much losses you have in your circuit and what happens if you move away from your center frequency, right? Okay. Obviously, that's very critical when you are working with resonance circuits and filters. Okay. Now, supposedly, these kind of circuits are not resonance circuits. Right? The kind of situation that we have here is not exactly an resonance situation that we worry that much about Q. Nevertheless, Q is a very important factor when you design tuned circuits. Basically, if you have a tuned circuit and you have a filter, all right, Q defines the bandwidth of this. Okay? So the higher the Q, the narrower your bandwidth. Supposedly, in all these circuits here, transmission line wise, they are supposed to be flat with frequency. In other words, the bandwidth is very large. As it turned out, that what limits the bandwidth in transmission line circuits, not the resonance ones, okay, the regular ones, is not the losses as much as it is the excitation of higher order harmonics, higher order modes, higher order modes. And when you are told this cable here or that transmission system is good for 12 gigahertz, that means above the 12 gigahertz you have higher order modes, and therefore you start to have serious mode dispersion, right? And mode dispersion is a form of distortion that happens to your communication system and hurts your fidelity of your signal that you are sending, especially if you are doing digital communications. Right? So that's really what limits the bandwidth, right, rather than the Q. If you are designing a tuned circuit, then obviously the Q is what limits your bandwidth.
Also, on the Smith chart, if you have Q equal to 1, 2, 3, those arcs you can draw.
I can't hear you.
You can draw arcs on the Smith chart that show you different Q levels. So if you move from the center towards the outskirts, you get different Q. Right?
Talking about the eye shape.
Yeah. So you have like arcs that go from OC to SC and give you different Q levels as you go from the center to the outer one.
Okay, I see what you're saying. Okay, I'm not familiar with that. I can
I've seen some Smith charts that show us that too, but just to give you an idea of what the Q will be if you use different matching.
But what's the Q here? What's meant by the Q in this case? If you have a
the selectivity of the matching network. Like if the matching network has some
Q of the matching network.
okay.
Q of the matching network. I see you now. I see what you're talking about now. Okay, so we're talking about Q for a situation where you have a stub, right? Okay, because this is good for a certain distance based on a certain frequency. So if you move off that frequency, I see your question now. Initially, I thought about you talking in general about Q transmission lines circuits. Obviously, you know, this is designed now for a particular frequency because the length of the stubs are portions or related to the wavelength, and the wavelength is at that particular frequency. So if you move away from that frequency, your matching network is no good, right? I see your question.
So basically it's really high.
Hmm?
So it's like a high Q then. Because you're moving away from it, it's going to attenuate, right?
Well, obviously the quality of the match is gonna be off if you move from that point. Yes, it will be like a high Q situation. Right. I see your question now. That's a good point. I didn't cover that in my chapter, so I'm going to add that. Thank you. That's the end of the transmission line chapter. I want to move into the waveguides and the scattering parameters. And I've been debating which one to go into first, right? And I'm thinking about covering the scattering parameters first instead of covering the waveguides. Although in the syllabus we said we'll cover the waveguide first. And that will give me a chance to work further in my notes that I'm going to release to you on the waveguides. Okay? So when we cover the scattering parameters, it helps also with the analysis of waveguide components later on. So after we cover the waveguides, I'm going to do something simple in the 20 minutes left here about waveguides, but next lecture we'll be starting the scattering parameters. Let's show the concept of waveguides first, and then we'll go after that into scattering parameters. You recall plane wave propagation. That was one of the chapters that we covered in undergraduate fields. And basically, that's what we have so far in the transmission line. The models that we have developed, the RLCG models for the transmission line, are based on the propagation of what we call plane waves. All right? And the higher order modes are being ignored. The concept of plane waves is when you have a source, your source is sending a wave in a uniform fashion in one dimension, right? And the cross section is uniform. And that's really what we assumed in the transmission line case. When we talked about transmission lines, we assumed that the E field goes like that, and the H field goes like that, okay? And this repeats on all cross sections, okay? There's nothing that's going to change in this regard. This is what we call plane wave. And the equation for the solution here was V, for example, is equal to V plus e to the minus gamma z plus V minus e to the plus gamma z, and which we wrote in the time domain as V of z and t as V plus magnitude cosine omega t minus beta z plus some phase V plus V minus cosine omega t plus beta z plus V minus. As we said, if we take one or the other, okay, and we study that, we are really studying the features of both, and we can resort to the superposition later on. So this one here is a wave and propagation. And the characteristics of this propagation is certain phase velocity, okay, which is basically, when you look at this equation here, at some instant t, and later in time it does that. Basically, it's the same exact wave, and the delta distance that we moved in the delta time that passed, all right? At this location here, you have a peak. At this location here, you have a peak. So it means omega t plus beta z are supposed to be the same. So omega t plus delta t plus or minus, I should say, beta of z plus delta z supposed to be the same exact phase as omega t plus beta or minus beta z. From that, we conclude that omega delta t is equal to beta delta z, and delta z over delta t is omega over beta, which is the phase velocity. We call it C phase. Right? Beta, as we discussed as well, comes out to be 2 pi over lambda, where lambda is the distance between two peaks on this waveform. So we have beta is 2 pi over lambda, and obviously omega over beta, which is the phase velocity, is equal to omega over 2 pi lambda, which means lambda f. So end up with lambda f is equal to c phase, and these are all characteristics of plane wave propagation. And that's basically the speed of light in that particular media, whatever the media is. Now, this can happen in waveguide, it can happen in a transmission line, it can happen in open space. If we have a plane wave, it's the same feature, because it's actually controlled mathematically by this equation. That's the equation of a plane wave propagation. There's no function here except for z. There's no x and y variations, right? There's no x and y variations. So based on that, let's assume now that I have a plane wave that I'm going to propagate in open space. Let's assume it's open space now. No mu, no epsilon, just mu naught and epsilon naught, just for the sake of convenience. And I'm going to denote all the peaks with pluses and all the valleys with minuses. So here's a plane wave propagating along the z-axis, and I capture that at some particular instant in time. So I'm fixing t. Here's t. I will have the following. I'll have pluses that are spaced by lambda, and minuses halfway in between.